Okay, so last example here on expected value, and with an example question. At a games arcade, you have to pay €2. So remember, what you have to pay is important to play a game of chance. In this game, 2 dice are thrown. If the total of the numbers on the 2 dice is 2, 3, 4, 10, 11, or 12, you double your money. Okay, so you get €4 back. If the total is 5 or 9, your stake, €2 is returned to you. So you win €2. You come out with nothing, but you win €2 out of the game. However, if the total is 6, 7, or 8, you lose your stake. Okay, so you lose €2. What should the random variable x be for analysing the game, and what are the possible values of x? Okay, so my random variable is x. I could make a table here that had 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, that's going to be a massive table. Okay, instead I can group them together, because for 2, 3, I'm just going to change colour. For 2, 3, 4, 10, 11, and 12, you would win exactly the same amount of money. For 5 and 9, you win the same amount of money. And for 6, 7, and 8, you would win the same amount of money. So while I could make a table that had 2, 3, 4, 5, 6, 7, 8, and all the way up to 12, and then I would have, I'd win €4 for 2, €4 for 3, €4 for 4, and calculate their probabilities. Okay. Instead, I can make a much simpler table by grouping those together. Okay. So if my total amounts to 2, 3, 4, 10, 11, or 12. So if it amounts to any of those numbers, I'm winning €4. Okay, my x is €4. All right. If I get a 5 or a 9, my stake is €2. And if I get a 6, a 7, or an 8, I lose €2. So minus the €2. I don't get my €2 back, in other words. Okay. So sometimes it's easier to group them. Like I said, you'll get the exact same thing by doing a long table with each of your individual numbers and writing 4 beside the 2, the 3, the 4, the 10, the 11, the 12, writing €2 beside 5 and 9, writing minus €2 beside 6, 7, and 8. But then you've got a huge number of probabilities, first of all, to calculate, and a huge number of calculations to do. Okay, so hopefully that makes sense there in grouping them with the same values. So 2, 3, 4, 10, 11, and 12, for each of those I would get the same value. For 5 and 9 I get the same value, and for 6, 7, and 8 I get the same value. Okay, so now I have to calculate my probabilities. Okay, and I'm talking about 2 dice being thrown. Okay, and I'm totaling the numbers. So 2 dice being thrown, or whatever it is, if it's 2 dice in a spinner, if it's 2 things, I can always make a two-way table. Okay, so again, I've got 1, 2, 3, 4, 5, 6. And filling out my two-way table. So I've got 1 and 1 is 2, 1 and 2 is 3, 4, 2 and 1 is 3. Okay, so I am looking at getting a 2, 3, 4, 10, 11, and 12. So if I get any of those numbers, I get €4. So I get a 2. So if I look at all of the numbers here, so I can count 2, 3, 4. Was it 2, 3, 4, 10, 11, or 12? Okay, so 2, 3, 4, 10, 11, and 12, and that should be all of them. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that is 12 out of 36. So just remembering here, this is my probability now of x. Okay. If I was to get 5 and 9, so the probability of getting either 5 or 9, let's go for pink. So 5 or 9. Okay, now you can obviously count them. I'm just doing this to make it really obvious. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the probability of getting a 5 or a 9 is 8 out of 36. And again, you can simplify these if you want. And the probability of getting a 6, 7, or an 8, and you'll see, okay, it looks like an awful fair game when you're looking at it. Like you've got 2, 3, 4, 10, 11, and 12 you win with. But look at all of the numbers now that you actually lose with. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so there are 16 out of 36 that you can actually lose with. And just to point out that, remember, it is probability, and these games are designed for the person playing them to lose. Okay, so they're designed with the most frequent probabilities being the ones that you lose on. Okay, so even though we've got more numbers here, we've got 2, 3, 4, 10, 11, and 12 that you actually win the biggest amount on. Okay, so that makes it seem like, God, this is really fair. There's loads of numbers you can win on, but there's actually much more 6, 7, and 8 than there is all of those numbers together. Then remember, you are saying x px. Okay, and also remember that all of these px's have to add to 1, so it's kind of a nice easy way of checking. Okay, so x px, when you multiply 4 by 12 over 36, okay, do that on your calculator, you'll get 2/3. Remember, this is money, even though you are getting fractions. Then you get 4/9, and it's minus €2, so minus 8 over 9. Okay, or you can turn them in decimals either, rather than writing them as fractions in euro. You can actually write them in decimals. Okay, and then at the very end, I get 2 over 9. Okay, so 2/9, or, okay, I'm now going to use decimals for this. It's 0.22. Okay, or 22222. Okay, remembering now that it costs me €2 to play the game, so subtract €2 from that. Okay, and I have minus 1.77, or 78 actually when I round it, 1.78. Okay, so from playing this game, again, just to explain what that minus 1.78 means, that for a large number of people playing this game, you would expect that per person they would lose 1.78. Okay, now remember, people will win this game. People will win the €4, they'll get their money back, and they'll lose the €2. But on average, okay, for a large number of people playing this game, that you would expect to be up. So the person that designed the game would expect to win back €1.78 from each person that plays the game. Okay, so if 1,000 people were to play the game, I'd have 178 times 1,000. I'd be looking at winning. So if I designed this game, I would be looking at earning 1,780 if 1,000 people were to play this game. Okay, so it is favourable to the person that designed the game, unfavourable to the players. Okay, so it is unfavourable to the players. Okay, now the next bit's a tricky part of the question. It says calculate the entry fee that would make this game a fair game, assuming that you win €2 for a total of 2, 3, 4, 10, 11, and 12. So you're not necessarily doubling your money here. You are just winning €2. And your entry fee is returned of a total of 5 or 9. And you lose for the others. Okay? So, okay, I have to design a new table here. Okay? So I don't know the entry fee. So this is for the third part. We don't know the entry fee. Okay, so let's say it costs us €Y or X, whatever you want, put a letter on it. Okay, I don't know what the entry fee is to win. Okay, so I'm going to do out my two-way table again, which will be quite similar to the last one, but with one really important difference. Okay, X, PX, and XPX. Okay, so if the total is 2, 3, 4, 10, 11, and 12, you had 12 over 36, remember from the last time, so 12 over 36, or it'll actually be easier maybe here to use the simplified fraction, so 1/3. If you have 5 or 9, okay, it was, can't remember what it was now. It was 8 over 36. Okay, so simplify that down, get 2/9. And if you get 6, 7, and 8, I'm going to get 4/9. Okay, so if I get 2, 3, 4, 10, 11, and 12, I am still, oh sugar, I've after writing my probability in the wrong section, apologies. If you did that, very easy, just switch the top. I'm going to just, okay, so sorry, my probability should be in the PX section. So my X, if I get 2, 3, 4, 10, 11, and 12, I'm still winning €2, so I'm not doubling my money. Okay, I'm just winning €2 here, whatever it is, whatever the entry fee is. Okay, I'm specifically going to talk about what I actually win in this table. Okay, and it will be rare that you have to do this, but when you don't know the entry fee, okay, I'm going to specifically talk about what I actually win. So I would win €2 here. For a 5 or a 9, I actually win nothing, but I lose nothing either. Okay, so I'm just at 0. Okay, now before we used, so up here, and most of the time, okay, for a straightforward question, you will use the €2, okay, because I get back the €2. Okay, for this one, I'm specifically talking about what I'm winning because I don't know the entry fee. So I don't know the entry fee, which means I obviously won't know this number here. And I want to limit the amount of variables I have. So I'm talking about only the amount that I actually win. Okay, so I win €2. My entry fee is 0. And for 6, 7, or 8, I would lose the entry fee. Okay, so I lose Y. Okay. Like you could have this the same as the last time, and you could have Y plus 2. So you could have that, and you could have plus Y, and you could have 0 that you wouldn't win anything. But honestly, it is easier when you've got an unknown to talk about just specifically what you're winning. Okay, it does cut down your variables massively because now by saying a 5 and 9, you win nothing. Okay, because you just get your money back, so you're not winning anything or you're not losing anything. But for 7, 8, for 6, 7, and 8, I do actually lose the entry fee. I lose Y. This just limits the amount of variables because I've now got only one variable rather than trying to think of 2 variables. XPX, then I'm still just multiplying. So 2 over 3, 0, and minus 4 over 9. Okay. I am going to add them together. So I've got 2 over 3 plus, so it'll end up being minus 4 over 9 plus 0, but I'm not going to put that in. Okay, or 4y over 9, apologies. Okay. If it's a fair game, and this is a really important bit for this question, if it's a fair game, it has to be equal to 0. Okay, that this expected value should be 0. Okay, I neither win nor lose anything. So the person that designed the game is not up, the person that plays the game is not up. Okay, so I've got 2 over 3 is equal to 4y over 9, and by simple algebra I get that y is equal to €1.50. So a fair entry fee to this game would be €1.50, and then it would be a fair game. Okay, so again, spend time with this question, especially this second part, and try and understand the way I've changed the table this time, okay, and the difference between the two tables. And again, if any questions or if you're not sure, please ask.